This is Dr. Khan, professor of chemistry at Penn State, and I'm going to be your instructor for this course and begin with chapter 14, which is chemical kinetics. Kinetics deals with rate of reaction, how fast a reaction is going on or how slow a reaction is going on. Here, this is a simple analogy. If somebody is walking and say walks only 10 feet, must not be a very good walker, must be a very lazy walker, and he travels 10 feet in 2 minutes. So what would be his rate of walking? The final position, let's look at final position here, and initial position is here. So the distance between final and initial, if you subtract, that would be 10 feet in this case as an example. That's change in position, change in location, divide by the time, delta t. So change in position would be 10 minus 0 divided by 2, that's the 2 minute. So that speed comes out to be 5 feet per minute, 10 divided by 2 per minute. In a similar manner, we can get rate of a chemical reaction in terms of concentration change. Final concentration minus the initial concentration divided by the time. So change in concentration we express with delta. Delta stands for change. Divide by change in time, which is 2 minutes. Now why you call it change in time? Whenever you start your watch, say you have a stopwatch, and that's your zero time, and when you stopped your watch, say it was 2 minutes, so obviously the difference is 2 minutes. And so change in concentration over time gives you rate of reaction. Now I want to point out to you that H2O2 reaction, which you're seeing here, H2 and O2 will be depleting as reaction goes on. So that means the concentration would decrease for H2 and O2, and concentration is going to increase for H2O because it builds up with time. So we show that difference by assigning a negative sign in front of rate of hydrogen, or it's called dissipation of hydrogen or oxygen. In this slide, there are 3 runners, John, Tim, and Susie. Now the question is, when there are 3 runners running, how many rates would you expect? Obvious answer would be 3, because they're independent runners and they can run, and obviously their speed or rate can be expressed by 3 expressions. Again, distance over time. So if there are 3 runners, then you'd expect 3 such rates. If there are 3 chemicals in a reaction, then obviously there'll be 3 different rates expressed for those 3 chemicals. So in case of H2O2 giving H2O, so H2 is one of those chemical, O2 is the second chemical, H2O is the third one. So the rate for H2, remember the change in concentration would be delta H2 over delta T, that's by time, or final minus initial, that's delta H2, divided by time interval. That gives you rate for hydrogen. Now don't forget that we assigned a negative sign because hydrogen concentration is depleting. That means final value is always smaller than the initial value. Because let's think about that you started with 5 moles of hydrogen. Say after 2 minutes you have only 3 moles left. So it'd be 3 minus 5, that's minus 2. So keep that in mind. So both in case of hydrogen and oxygen, the concentration is going to decrease. That's why there's a negative sign. On the other hand, product builds up with time. So H2O, whatever initially you have, it is going to go up. Say initially I had no H2O because it's the product. After some time I may have 5 moles. So my difference is 5 minus 0, that's plus 5. So in case of product, it's positive. The change is positive. So this is positive. I don't need to show any sign, but just at the beginning I wanted to remind you this. Product concentration always goes up as the reaction happens, and reactant concentration goes down as the reaction happens. So in case of reactants, we assign negative sign, and obviously in case of product, it will be positive sign. Now question is how these three rates are related. So when John, Tim, and Susie are running independently, can we relate their rates? Definitely, once we know the rates, then we can always find out some kind of a relationship, whether Tim is running 2 times faster than John, or Susie is running about the same speed as Tim, but there could be a relationship. And same is the case in a chemical reaction. When reactions take place, we know their rates and we can compare their rates. Let's first assume that these rates are equal. So this is the first one is rate of dissipation of hydrogen. Next one is rate of dissipation of oxygen. And third one is the formation of H2O. Now initially we set them equal, but we know that they're not equal. How do I know that? Look at the reaction itself. There is a 2 in front of H2. What that means is hydrogen is dissipating 2 times faster than oxygen because there is 1 in front of oxygen. So those determine the rates. Similarly, formation of water will be 2 times faster than that of oxygen. So in any chemical reaction, a stoichiometric ratio has to be maintained. In this case, 2, 1, and 2. 2 in front of hydrogen, 1 in front of oxygen, and 2 in front of H2O. And that has to be maintained. So that means hydrogen is disappearing 2 times faster than oxygen, and water is being formed 2 times faster than that of oxygen. Now, we all know that when I say 2 times faster for hydrogen than oxygen, we all know that 2 cannot be equal to 1. In order to set them equal, I have to divide 2 by 2. Exactly the same thing you're going to do in order to set them equal. Since hydrogen is dissipating 2 times faster, so I divide by 2. And then it would be equal to that of oxygen dissipation rate. Similarly, H2O is being formed 2 times faster, so divide by 2 to set them equal to that of oxygen. So this is the rate relationship among all these reactants or products in this reaction. So keep this in mind that you can find out relationship between rates by looking at basically coefficients of balanced reaction. In this case, 2, 1, and 2. So basically what I would do, I'd first write down the rate and then divide by the coefficient, which is 2 in case of hydrogen. Then get the rate for oxygen, divide by 1. Write down the expression for H2O and divide by 2. And that's this expression. It's very important, and there are lots of problems that I have assigned that uses this expression. Now, rate of reaction also depends upon how many of those reactants are present. Let's assume that in one container I have H and Cl, and that product is HCl. So in other words, H plus Cl, I selected this atomic reaction just for a simple example. HCl cannot form unless and until they come close to each other. Now think about how likely it is having one hydrogen and one Cl in a box. They would, in a box of fairly decent size, can come close to each other so that they can make a bond and give you product HCl. So that product formation is like shaking hands. You can't shake a hand with your friend if that person is far away from you. So same thing is true for a chemical reaction. These two reactants will have to come close to each other. Now, how likely it is? Think about now your box is fairly decent size, say one room, the size of a room, and I have one H and one Cl there. How likely they would come together? Very unlikely, because there are many other molecules there all over. other than HNCl. Or even if you think that it's a vacuum, it's not much likely that one H and one Cl would come close together to give the reaction product. Now instead of one, say I have three. That means I now three of hydrogen and one of Cl. Now obviously now probability of meeting is 3 times faster than case A. Instead of 3, I have 3,000 of H. Obviously now it's 3,000 times more likely. So in other words, probability of reaction increases with number. If I have, say, 3,000 hydrogen, 3,000 Cl, obviously it would be probabilities also increase in a multiplicative manner. So we express rate with another expression which is based on concentrations. Now this is how we can write down the second rate. Concentration of reactant 1, concentration of reactant 2, and they should be multiplied together. Also, there is a constant. We call it rate constant, K1 in this case, for the first reaction, which deals with dissipation of hydrogen. Also, concentration is raised to the power A, and for oxygen is raised to the power B. These are called orders of reaction, and these come from an experimental data. So without doing an experiment, you cannot predict whether it's going to be A is going to be 1 or 2 or 1.5. So order of reaction has to be known from experiments or from experimental data. Similarly, for this reaction with oxygen, again I can write down in terms of H2 concentration and O2 concentration. Remember, H2 and O2 will have to come close to each other. Probability increases as the number increases, and that's incorporated in this expression. That means you product the concentration. Concentration is nothing but the number per unit volume, number of moles per liter, for example. Now in case of H2O, again, this is one way of writing down rate expression, which I already discussed in terms of concentration change, and we can write it for every chemical. And this is the second way of writing down the same rate in terms of a constant, which is the rate constant, times the concentrations of the reactants. So this is how you can write down all these three rate expressions. And what is different here, H2O2 are the same, but here is the different rate constant. That's going to be different for different chemicals or different compounds. Now A when equals to 1, A or B equals to 1, we call it first order reaction. So the power is 1 in this particular case, so we're dealing with now first order reaction where A gives products. We're assuming that A is just one of the chemicals. In general, I mean, that's how you'd expect. So in terms of concentration change, it's going to be minus delta A over delta T. And in terms of concentration of reactant, it'd be K times A raised to the power 1. Keep in mind, collision is needed. In this case, there'd be lots of A molecules in the reaction volume, and they would collide with each other. And finally, when they have enough energy, then reaction is going to happen. That's how first order reaction happens, and that's why it's raised to the power 1. Those of you who are good in math, this is a differential equation, so I just want to give you the little background of that, but you don't have to know it for this course. It's like dA over dt equals to K and A concentration. And if you know how to solve it, if you solve it and apply two limiting conditions, A0 is for concentration as time equals to 0. So let's write down here, when time equals to 0, that's initial concentration. AT is the concentration at a later time, T equals to T. Then you get this log of AT by A0 equals to minus KT. Now this is a very useful expression. This is often used in calculating expiration dates for, say, medicine. You know the initial value, and after some time, what could be the value of the active ingredient. If it's a first order reaction, you can apply an expression like this. Only thing you need to know is the rate constant that comes from somebody's experiment on that compound. Here we're going to discuss half-life. Now, at the beginning there are 8 bars. 2 days later, you see that there are 4 bars left. That means in 2 days, the number of bars has decreased from 8 to 4. Now you can see who is responsible for that on the right hand side. After 2 more days, you see that there are only 2 bars left. So what is going on here? The half-life is 2 days. So it's the time interval when the number is decreased to 1/2 of its original value. Similarly, in chemical reaction also, we define half-life as the time when the concentration is reduced to 1/2 of its original value. You can readily get an expression for half-life for first order or second order reaction. Remember, for first order reaction, there is an expression like this: log of AT over A0. Keep in mind, this is a natural log with respect to base E, not base 10, equals to minus KT. T is the time, K is the rate constant. Now, if I want to calculate half-life expression when T is equals to T half, AT is going to be A0 over 2. I already defined that because this is the time when concentration is reduced to 1/2 of its original value. So by substituting AT by A0 over 2 and then basically get log of 1/2 equals to minus KT, you end up with this. Of course, T is T half because that's the time, half-life. That's how we label that time. So you get 0.0693. So 0.693 over K. That's the half-life for first order reaction. For a second order reaction, the expression is like this: 1 over AT equals to KT plus 1 over A0. Again, we can do a little math. AT would be A0 over 2, and if after the little algebra, this is what you end up with for second order reaction. Remember, second order reaction, here order is going to be 2 instead of 1. For first order is 1, the second order is 2. So if you calculate the half-life, it's going to be 1 over K times A0. So here the half-life depends upon initial concentration. On the other hand, in case of first order reaction, let me show you with asterisk. The first order reaction half-life is independent of initial concentration. So it doesn't matter how many, what moles per liter you begin with. Half-life is going to be the same for that particular reaction. Now here we're showing you activation energy or energy barrier involved in a chemical reaction. If I just put all 2 or 3 chemicals together, there'll be no reaction until and unless we provide enough energy. Think about any reaction. Let me give you one example: H2 plus O2 giving H2O. So if I want to balance it, 2H2 plus O2 giving H2O, 2H2O. Now this reaction, when you just put hydrogen and oxygen together, is not going to happen. So you have to provide enough energy so that that hydrogen and oxygen not only come close together, they can also react. And this is how we explain this reaction. This is the energy diagram. So initially all the reactants are here. And when you provide enough energy, they go to the maximum of this energy barrier and then go to the other side. So other side, you have products. So in other words, you must provide enough energy so that reactants can go from reactant side to the product side. And we call it activation energy. It's like you have your friend's house on the other side of the hill. If you can't climb on that hill, obviously you cannot go to the other side to your friend's house. So in other words, you must have enough energy to go to the top of the hill and then slide down to the other side. Same is the true in case of a chemical reaction. You must provide enough energy for the reaction to happen so that it can go from reactants to product side. Now, there is an expression given by Arrhenius, who is a scientist. I'm highlighting that that expression. Log of K1 by K2 equals to EA. EA is nothing but activation energy, which is nothing but barrier height, or you can call it height of the hill. EA over R. R is the constant, ideal gas constant, which is 8.31 joule per Kelvin times moles. In this particular case, we're going to use this value and these units. That's the energy units, since our calculation involves energy. So keep in mind 8.31 joule per Kelvin times mole. And K1, again, this is the rate constant at temperature T1, because rate constant changes with temperature. So this is for at temperature T1, and K2 is at temperature T2. You have to be very careful about these. So that's T2 is the temperature, second temperature, T1 is the initial temperature. Basically, by raising the temperature, we are providing enough heat so that reactants can go to the product side. So this is how you can calculate activation energy. And I want to remind you that temperatures are in Kelvin, not in degrees centigrade. So if you have temperature in degrees centigrade, you can add 273.1 to get it in Kelvin. So these are all inverse of temperature 2 minus inverse of temperature 1. Enzymes, here we have a little discussion of enzyme. Enzymes are biological catalysts. Now, again, those of you haven't studied about catalysts, let me remind you this. Catalysts are substances that enhance a reaction rate. Sometimes they also can slow down a reaction rate. Like in case of in medicine, in the field of medicine, if you don't want certain reaction to happen, then you'd like to slow down that particular reaction to slow down. So enzymes are nothing but biological catalysts. When enzyme enhances rate of reaction, that basically cuts down the height of the hill. So initially, if this is the hill, height of the hill, or activation energy, what enzyme does, or catalyst does, is going to cut it down to a smaller value. So that means when reactants are sitting here, see all reactants are here on the left side, whenever it sees a small hill to climb, it can readily go from reactant side to the product side. So that's how enzymes or catalyst, biological catalyst, enhances rate of a reaction. Now you probably heard about lock and key model of enzyme. So basically enzyme doesn't work on anything and everything. There is specific enzymes or specific catalyst that only helps in specific reactions. I often give this example. In our saliva we have alpha amylase that breaks down starch into glucose, which finally goes to our bloodstream and gives us energy. Now, this is a catalyst, keep in mind. So it makes this breakdown of starch possible. I mean, without this amylase in the saliva or coming from pancreas, the starch would not break down at our body temperature. Now, this amylase is not going to work with everything. We have many other things in our body, which from intake of food we can get it, but it doesn't break down everything. Like it would not do anything to cellulose or fiber. so fiber remains intact. In a way, it's good for us. Now, reaction mechanism, we give you some idea about reaction mechanism. It tells us how a reaction takes place. So different types of reactions have different mechanisms. And we already defined catalysis. Catalyst can increase or decrease the rate of reaction without itself being consumed, because they are not consumed. You can always get back catalyst. Now, catalyst could be a following type: homogeneous, the single phase. You do not even understand whether something is in the solution or not. Like alpha amylase is soluble in water, so if I put alpha amylase in water and a starch, you do not realize that enzyme is there, because it's the homogeneous is completely soluble, so I don't see any distinct phase. On the other hand, there are heterogeneous catalysts too. In many reactions, scientists use heterogeneous catalyst. For example, solid nickel acts as a catalyst in this reaction between these two gases, ethylene and hydrogen. When they react, they give ethane.